Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over paper 1, i.e. the multiple choice questions from the 2015 SQA Higher Physics exam paper. Now there are 20 questions in this section and I recommend that you try them yourself before looking at these solutions. So let's get started. Question 1 says the following velocity time graph represents the vertical motion of a ball. So we have velocity in meters per second on the y-axis and time in seconds on the x-axis, and you can see the ball starts off at a velocity of 19.6 meters per second, then reaches 0 meters per second after 2 seconds, and then after another 2 seconds reaches minus 19.6 meters per second. It then says which of the following acceleration time graphs represents the same motion. So we're basically just trying to find the corresponding acceleration time graph for the velocity time graph that we're given. Well, if we look back at the velocity time graph, you can see that the graph shows a uniform deceleration, which is shown by this negatively sloping line on the velocity time graph. And we can say that on an acceleration time graph, this will be a constant negative acceleration. And that's because our gradient, remember, is negative here and not positive. So if we look back at our options, the only graph here which shows a constant negative acceleration is this one here, graph C. And you can see the value of acceleration is negative 9.8. And that's because the velocity time graph is shown for the vertical motion of a ball, where the ball is being thrown upwards into the air. So it's going to have gravity acting downwards on it, and therefore an acceleration due to gravity acting downwards, which always acts at minus 9.8 meters per second squared. So we can say here the answer is C. Question 2 says a car is travelling at 12 meters per second along a straight road. The car now accelerates uniformly at minus 1.5 meters per second squared for 6.0 seconds. The distance travelled during this time is... Well, notice how we're given an initial speed, an acceleration and a time, and we're asked to find the distance travelled. So we're going to be using equations of motion here, so let's write down suvat first so that we can decide which equation of motion to use. So we're trying to find the displacement or distance s. We know that the initial speed u is 12 meters per second. We don't know what the final speed is. We know the acceleration is minus 1.5 meters per second squared, and the time is 6.0 seconds. So I'm going to put a star next to s because that's the one I'm trying to find. And you'll notice we want to use the equation of motion that does not have v in it. So looking at your relationship sheet, that one is going to be s equals ut plus a half at squared. And we can then sub in the numbers to get what s is. So we have 12 times 6.0 plus a half times minus 1.5 times 6.0 squared. And putting all of this into your calculator should give you an answer of 45 meters, which gives the answer B. Question 3 says a box of mass m rests on a slope as shown. So we have our mass m on this slope which has an angle of theta to the horizontal. Which row in the table shows the component of the weight acting down the slope and the component of the weight acting normal to the slope? Well, you should remember that the component of weight acting down the slope or parallel to the slope is given by this expression mg sine theta, whereas the component of weight acting normal or perpendicular to the slope, which is this component here, is given by the expression mg cos theta. And that's found knowing that the component going straight down is going to be just mg. So we can say we should have mg sine theta and mg cos theta, which gives the answer A. Question 4 says a person stands on bathroom scales in a lift. The scales show a reading greater than the person's weight. The lift is moving upwards with constant speed, downwards with constant speed, downwards with increasing speed, downwards with decreasing speed, or upwards with decreasing speed. Well, I'm going to start by sketching a little diagram of our lift situation here. So there's my lift. There's my upward reaction force, which is also the same as the reading on the scales, and there's my weight downwards. And you'll see that I've drawn R, the reaction force, the reading on the scales, to be bigger than the weight downwards, and that's because we're told that in the question here that the scales show a reading greater than the person's weight. So I've drawn R to be bigger than the weight downwards. So if the reaction force upwards is greater than the weight downwards, then we can say that the unbalanced force must be acting upwards in this case. So we can say that F, the unbalanced force, goes upwards because we have a bigger force upwards than downwards. And since R is greater than W, we could say one of two things. We could say the lift could be moving upwards with increasing speed or downwards with decreasing speed. And that's because if you think about it, an unbalanced force acting upwards on the lift will cause it to either move upwards and gain speed as it moves upwards, or if the lift is already moving downwards, an unbalanced force acting upwards on it would cause it to slow down as it moves downwards, so decreasing in speed. But you'll see that upwards with increasing speed is not an option here. We have upwards with constant speed and upwards with decreasing speed. But we do have the option for downwards with decreasing speed, which is option D. So that is going to be our correct answer here. Question 5 says a car of mass 900 kg pulls a caravan of mass 400 kg along a straight, horizontal road with an acceleration of 2.0 meters per second squared. So there's the 900 kg car, the 400 kg caravan, and then the coupling between the two. Assuming that the frictional forces on the caravan are negligible, the tension in the coupling between the car and the caravan is. Well, usually in these connected system kind of questions, we would start by trying to find the acceleration of the whole system, but notice how we're given that in the question, so this is going to be a bit simpler than normal. So we can say we're already given the acceleration of the system, and therefore we want to find the tension due to the 400 kg mass, because that is the thing that is causing the tension in the coupling. So I'm going to use F equals ma now to find the tension, but I'm going to change it slightly to be T equals ma, where I'm calling the force my tension in this case. So using T equals ma, I'm going to use my mass of 400 kg times the 2.0 meters per second squared for the acceleration, and that gives me an answer of 800 newtons, which is option C. Question 6 says water flows at a rate of 6.25 times 10 to the 8 kilograms per minute over a waterfall. The height of the waterfall is 108 meters. The total power delivered by the water in falling through the 108 meters is, well, because we're asked to find a power and we're also given a time of per minute or 60 seconds, then you should be thinking along the lines of using the power, energy and time equation P equals E over T. But we don't have an energy yet in order to do that, so this is going to involve two parts, with the first part involving calculating an energy using some of the data we're given, and then calculating the power. Well, because the water starts off at a certain height and then falls through that height, we're going to be calculating the gravitational potential energy, EP equals mgh. So let's sub in the values that we're given. So we're given the mass of 6.25 times 10 to the 8 kilograms, times the gravitational field strength on Earth, which is 9.8 newtons per kilogram, times the height of the waterfall, which was 108 meters. So putting that into your calculator should give you an answer of 6.62 times 10 to the 11 joules. And now we can calculate our power using P equals E over T, but I'm just going to label it EP because that's what we used for our energy here. So subbing in the numbers now, we get 6.62 times 10 to the 11 divided by 60 because our time was per minute or 60 seconds, and putting that into your calculator should give you an answer of 1.10 times 10 to the 10 watts, which you'll see gives the answer B. Question 7 says a spacecraft is travelling at a constant speed of 0.6 c relative to the moon, so that's 0.6 times the speed of light. An observer on the moon measures the length of the moving spacecraft to be 190 metres. The length of the spacecraft as measured by an astronaut on the spacecraft is... Well, notice that it's asking us to find the length of the spacecraft measured by an astronaut on the spacecraft. So in other words, the astronaut on the spacecraft is in the same frame of reference as the spacecraft itself. So they're going to be measuring the proper length L, which means we're given the value here for the contracted length L dash or L prime, which is 190 meters. So using our equation for length contraction, we have L dash or L prime equals L times the square root of 1 minus V over C squared. And remember, we're trying to find L, so we can sub in the rest of the numbers to get 190 equals L times the square root of 1 minus 0.6 C over C squared. And notice how the C values here will cancel out. So we simply need to do 0.6 squared, then 1 minus that answer, then take the square root of that answer, and then to find L we can just do 190 divided by that answer that you'll have in your calculator. So we end up with L equals 237.5 meters, which is approximately equal to 238 meters if we round up, which gives us the option C. Question 8 says a siren on an ambulance emits sound at a constant frequency of 750 Hz. The ambulance is travelling at a constant speed of 25.0 meters per second towards a stationary observer. The speed of sound in air is 340 meters per second. The frequency of the sound heard by the observer is... Well, notice firstly that this is a question on the Doppler effect, so let's write down our equation for the Doppler effect, which is FO equals Fs times V over V minus Vs. And you'll notice that I've chosen to have the negative sign in the denominator and not the positive sign, and that's because we're told in the question that the ambulance is moving towards the stationary observer. So a little trick that you can use to remember which sign to use when is the phrase towards is take away and away is add. So it's moving towards, so I'm going to take away in the denominator. So I'm trying to find FO here, the frequency of the sound heard by the observer, so let's plug in the rest of the values here. So we have 750 Hz for the sound source frequency times the speed of sound in air 340 divided by 340 minus 25.0. And putting that into your calculator should give you an answer of 809.5 Hz, which we can round up to approximately 810 Hz, which gives us the answer E. Question 9 says the emission of beta particles in radioactive decay is evidence for the existence of. quarks, electrons, gluons, neutrinos, or bosons? Well, you should remember that beta decay or beta particles provide evidence for the existence of neutrinos. Moving on to question 10, it says two parallel metal plates X and Y in a vacuum have a potential difference V across them. So there's plate X and plate Y, and there's the supply voltage V. Then says an electron of charge E and mass m initially at rest is released from plate X, so the electron's going to start on this plate here. The speed of the electron when it reaches plate Y is given by, and we've got lots of different expressions that it could be. So let's think about what's going on here. The electron's starting off at plate X, which is negatively charged because it's connected to the negative terminal here, whereas plate Y is positively charged. So that means the electron will want to be repelled away from X and attracted towards Y. And the electric field in this case will go from the positive to negative, so the electric field will actually act in the direction from plate Y to plate X, from right to left. So therefore, when the electron is moving in the electric field, work must be done to it in order to move it against the electric field. And when the electron moves from plate X to plate Y, it's going to gain kinetic energy. We can start by saying that the work done on the electron is equal to the change in kinetic energy. And let's expand this right hand side to say what the change is. So it's going to be the final kinetic energy minus the initial kinetic energy. But remember, we're told that the electron starts from rest, so we can therefore simplify this to say that EK initial is equal to 0 since it starts at rest. So now we essentially have W equals EK final. So let's put in some expressions for both of these terms. So we know that work done is equal to QV, W equals QV from the relationship sheet, and we also know that kinetic energy EK has the expression 1/2 mv squared. I'm not going to put any subscripts on this because I only have one kinetic energy here, I don't have two. Now you might remember the question said that the charge in an electron is given by the letter E, so we're going to rewrite this as EV equals 1/2 mv squared, since the charge is the electron charge E. And we're asked for the speed of the electron, so we're going to rearrange for v squared, and then take the square root in order to get v on its own. So let's multiply both sides by 2 to get rid of this fraction, and then divide by the mass. So we get v squared equals 2ev over m, and let's take the square root to get v equals the square root of 2ev over m, which gives us the answer B here. Question 11 says a potential difference of 2 kilovolts is applied across two metal plates. An electron passes between the metal plates and follows the path shown. So we have the electron travelling straight until it reaches the region between the electric field, and at which point it's going to start curving up the way towards the positively charged plate. And we have a plate of 0 volts down the bottom, which you could think about as being a negatively charged plate. So positively charged on the top and negatively charged on the bottom. And the question then says a student makes the following statements about changes that could be made to allow the electron to pass between the metal plates and reach the screen. Statement 1 says increasing the initial speed of the electron could allow the electron to reach the screen. Statement 2 says increasing the potential difference across the plates could allow the electron to reach the screen. And lastly, statement 3, reversing the polarity of the plates could allow the electron to reach the screen. Which of these statements is or are correct? Well, let's look at each statement in turn and decide which ones are true or false. So for the first one, increasing the initial speed of the electron could allow the electron to reach the screen. Well, if we look back at the picture here, in order for the electron to hit the screen, we want the work being done on the electron, causing it to curve and hit the top plate, to decrease. Because if we decrease the work done on the electron here, it's not going to bend as much, and therefore it's going to travel further and maybe hit the screen. So we can say that to hit the screen, the work done on the electron between the plates needs to decrease. So let's see what that means for the initial speed of the electron. So work done equals a change in kinetic energy, which is equal to the final kinetic energy minus the initial kinetic energy. And let's write this in terms of the expressions for kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. And therefore, if we increase the initial speed of the electron, i.e. increase this number here, then you're taking away a bigger number in this whole expression here. So that means that the work done value on the left will actually decrease if you increase the initial speed of the electron. So that means that that first statement is true. Statement 2, increasing the potential difference across the plates could allow the electron to reach the screen. Well, remember another expression for work done is W equals QV, so since the electron charge Q is a constant, that value stays the same, and if we increase the potential difference across the plates V, then that means the work done will increase. But remember, looking at the diagram, we said we want the work done to decrease in order to allow the electron to not curve as much and hit the screen. So increasing the potential difference is actually going to increase the work done and therefore have the opposite effect to what we want. So we can put a cross next to that one. Lastly, reversing the polarity of the plates could allow the electron to reach the screen. Well, looking back at the picture, all that reversing the polarity of the plates is going to do is going to have, say, 2 kilovolts down here and 0 volts up here, which means that the electron will curve down the way. It's not going to cause it to be deflected any more or any less. So we can therefore say that that one is false. So we have that one only is correct, which is the answer A. Question 12 says the following statement describes a fusion reaction. So we have hydrogen plus hydrogen going into helium plus a neutron plus energy. The total mass of the particles before the reaction is 6.684 times 10 to the minus 27 kilograms, and the total mass of the particles after the reaction is 6.680 times 10 to the minus 27 kilograms. It then says the energy released in the reaction is. Well, you should be thinking that this is a question on Einstein's mass energy equivalence, so we're going to be using E equals mc squared, but in order to use that we need to firstly know what m is, the lost mass. So to find the lost mass m, remember we take the total mass before the reaction and subtract the total mass after the reaction. So that gives us 6.684 times 10 to the minus 27 minus the 6.680 times 10 to the minus 27, which you can put into your calculator to get an answer of 4 times 10 to the minus 30 kilograms. And remember not to round anything in your calculator when you're doing these types of questions. So using the equation E equals mc squared now, we can plug in our mass to get 4 times 10 to the minus 30 times the speed of light squared, 3 times 10 to the 8 squared, and putting that into your calculator should give you an answer of 3.600 times 10 to the minus 13 joules, which is option D. Question 13 says 2 identical loudspeakers L1 and L2 are operated at the same frequency and in phase with each other. An interference pattern is produced. At position P, which is the same distance from both loudspeakers, there is a maximum. The next maximum is at position R, where L1R equals 5.6 meters and L2R equals 5.3 meters. The speed of sound in air is 340 meters per second. The frequency of the sound emitted by the loudspeaker is. Well, we're asked to find frequency, we know the speed of sound, and so you should be thinking that in order to find frequency, we're going to use V equals F lambda. But because we don't know what lambda is, we need to use this data here in order to find it. So for maxima, remember we have the expression path difference equals m lambda. So let's rewrite the path difference as L1R minus L2R equals m lambda, and let's put in our numbers. So we have 5.6 minus 5.3 equals 1 times lambda. Now I've used m equals 1 here because remember this is the central maximum in the middle, m equals 0, so the next maxima has got to be m equals 1. So that means I have 1 times lambda, or lambda equals 5.6 minus 5.3, which gives me lambda equals 0.3 meters. So now I can use this wavelength value in the equation V equals F lambda. So rearranging for the frequency F, we get V over lambda, and substituting in our numbers, we have 340 meters per second divided by the 0.3, which gives an answer of 1.1 times 10 to the 3 hertz, which you can see as answer D. Question 14 says an experiment is carried out to measure the wavelength of red light from a laser. The following values for the wavelength are obtained. So we have 650 nanometers, 640 nanometers, 635 nanometers, 648 nanometers, and lastly 655 nanometers. The mean value for the wavelength and the approximate random uncertainty in the mean is. Well, you'll notice we're given all of our answers in terms of nanometers, and we're going to start by finding the mean value for the wavelengths. So remember, to find the mean of a set of results, we simply take the sum of the measurements and divide by how many measurements there are in total. So what we do is we add up our 5 wavelengths and we divide by 5 because there's 5 sets of results. So if you put that into your calculator, you should get an answer of 645.6, which we can round up to 646 nanometers. And we've therefore narrowed our options down to C or D because those both have wavelengths of 646 nanometers. But we now need to find what the approximate random uncertainty in the mean is. So in this case, it's going to be either plus or minus 1 or plus or minus 4 nanometers. So to find the approximate random uncertainty in the mean, let's use the equation from the relationship sheet. Random uncertainty equals the maximum value minus the minimum value divided by the number of measurements. So in this case we had 5 measurements, so if we take our maximum value, that's going to be the 655 nanometers, and then subtract the minimum value, which is the smallest value of 635 nanometers, and then we divide by the total number of values here, which was 5 again. So if you put that into your calculator, you should get an answer of plus or minus 4 nanometers for our uncertainty. So if we were to write our mean plus or minus the uncertainty in absolute form, we would get 646 plus or minus 4 nanometers, and you'll see that this gives us the answer D. Question 15 says red light is used to investigate the critical angle of 2 materials P and Q. So we have our material P on the left and material Q on the right, and it says a student makes the following statements. Statement 1 says material P has a higher refractive index than material Q. Statement 2 says the wavelength of the red light is longer inside material P than inside material Q. And statement 3, the red light travels at the same speed inside materials P and Q. Which of these statements is or are correct? Well, let's look through each statement in turn and decide which ones are true or false. So statement 1, first of all, material P has a higher refractive index than material Q. Well, if we look back at the picture, let's draw on some normals here at this point where the light would exit the material, but it's not. It's actually being refracted such that it travels along this flat edge of the material. So let's draw on the normal here and the normal here. And remember, the critical angle is defined as the angle of incidence at which the angle of refraction is 90 degrees. And so in both of these cases, we've got the angle of refraction here being 90 degrees. And therefore, we need to look at the size of the critical angle in both of these materials to work out its effect on the refractive index. So material P, you can see, has a smaller critical angle, whereas material Q has a larger critical angle. So if we look at the relationship sin theta c equals 1 over n, which is the relationship between critical angle and absolute refractive index, then you can see that if we were to swap the n and the sin theta c round, we would have n equals 1 over sin theta c, and therefore the bigger the critical angle, the smaller the refractive index. So that means that material Q, since that has a bigger critical angle, will have a smaller refractive index than material P. So material P has a bigger refractive index than material Q, which means this first statement is true. So we can put a little tick next to that one. Statement 2, the wavelength of the red light is longer inside material P than inside material Q. Well, to answer that, we need to think about the relationship between wavelength and absolute refractive index, which is given by this expression here, n equals lambda 1 over lambda 2. Now remember, lambda 1 is the wavelength in air, so that's going to stay the same for the red light regardless, whereas lambda 2 is the thing that can change. So if we were to rearrange this equation for lambda 2, we would just swap the n and the lambda 2 round to get lambda 2 equals lambda 1 divided by n. But we've already concluded from the first statement that the refractive index in material P is greater than that in material Q. So we can say that lambda 2 is inversely proportional to n. So the bigger n is, the smaller lambda 2 will be, or the smaller n is, the bigger lambda 2 will be. So since n is greatest in material P, so then that means that the wavelength of the light in material P will be smaller than that in material Q. So that means that this statement 2 is false because it's actually the opposite that is true. The wavelength of the red light is smaller inside material P than inside material Q. Lastly, the red light travels at the same speed inside materials P and Q. Well, now we just need to think about how refractive index affects the speed of light in a material. Now remember, we have an equation relating refractive index and the speed of light in air and the speed of light in the material, which is this one here, n equals v1 over v2. So since the refractive index for the red light is different for the different materials, then that means that the speed of light in the material v2 is going to depend on n and the speed of light in air. And since the speed of light in air is a constant, it's just the refractive index n that will affect that speed of light in the material. But as we said, because the n values are different for the different materials, then that means v2 is going to be different for the different materials, and therefore the speeds are not going to be the same in the different materials. So we can conclude that that third statement there is also false. So this means that one only is correct, which gives us the answer A. Question 16 says the diagram represents some electron transitions between energy levels in an atom. So we've got E0 up to E3, and we're given the energy values for these energy levels, and we're given 5 different transitions here. It then says the radiation emitted with the shortest wavelength is produced by an electron making transition E1 to E0, E2 to E1, E3 to E2, E3 to E1, or E3 to E0. Well, firstly, we need to think about the relationship between wavelength and frequency. So remember, shortest wavelength means the highest frequency because the two are sort of inversely proportional. Lambda is proportional to 1 over f, which just means the bigger one is, the smaller the other one is. And remember, highest frequency means the greatest change in energy, since delta E is proportional to f. From the equation, delta E equals hf, or E2 minus E1 equals hf from your relationship sheet. So these two are directly proportional, which just means the bigger one is, the bigger the other one is. So that means I'm looking for the greatest energy difference here, which has got to be this one here, going from E3 to E0. So that means my answer is E. Question 17 says the output from a signal generator is connected to the input terminals of an oscilloscope. The trace observed on the oscilloscope screen, the Y-gain setting and the time-based setting are shown. So you'll see we have 1 full wave, 2 full waves and a half wave, so 2.5 full waves there, and the Y-gain setting is at 5 volts per division and the time-based setting is at 1 millisecond per division. It then says the frequency of the signal shown is calculated using the... Well, looking back at the picture here, remember frequency is found through the period t through the equation t equals 1 over f. And in order to find the period from the oscilloscope trace, remember that is using the x-axis or the horizontal plane on this diagram, and it involves counting how many divisions or boxes take up one wavelength. So in this case, one full wave is going to be 4 boxes or 4 divisions. And if we look at the options here, we've got the frequency of the signal shown is calculated using the time-based setting and the vertical height of the trace. That's false because remember we said it was the horizontal one. The time-based setting and the horizontal distance between the peaks of the trace. Well, if we look at the peaks of our trace here, you can see that going from peak to peak, that is going to be one wavelength, which is your 1, 2, 3, 4 divisions across. So we can therefore say that statement B is the correct one here because all of the others there are to do with the Y-gain setting. And remember, frequency and period are not found through the Y-gain setting, they're found from the time base. So the correct answer is B. Question 18 says a circuit is set up as shown. So we've got an AC source here and then a lamp, and it says the RMS voltage across the lamp is 12 volts. The power produced by the lamp is 24 watts. The peak current in the lamp is... Well, here in order to find the peak current, I firstly need to find the RMS current using some of the values that were given here. So we need to use a power equation given the RMS values here, and then we can use that in the equation relating peak and RMS current. So let's use the equation for power relating power, voltage and current. So we have P equals IV or P equals IRMS, VRMS, just to remind myself that I'm using the RMS values here. So let's sub in our values. So we get 24 watts equals IRMS times 12, and we can then divide both sides by 12 to get IRMS equals 2.0 amps. So we have IRMS equals I peak over root 2. Rearranging for I peak, I get I peak equals root 2 IRMS. And substituting in the numbers gives me root 2 times 2.0, which if you put into your calculator should give you a current of 2.8 amps. And you'll see that as the option D here. Now the reason that I had to do the power equation first in this question and then plug it into this expression relating RMS and peak current is because we can only use the power equation with RMS values. So we had to deal with the RMS values first, which is our normal kind of values, and then we had to find the peak current. Next we have question 19, which says a student makes the following statements about energy bands in different materials. Statement 1 says in metals the highest occupied energy band is not completely full. Statement 2, in insulators the highest occupied energy band is full. And statement 3, the gap between the valence band and conduction band is smaller in semiconductors than in insulators. Which of these statements is or are correct? Well, let's look through each statement and decide which ones are true or false. So statement 1, in metals the highest occupied energy band is not completely full. Well, that is true because remember the highest occupied energy band in metals or conductors is the conduction band, and it's not completely full because if it was, it wouldn't allow electrons to move around and conduct inside the conduction band, and that's what we need for conduction to take place. For statement 2, in insulators the highest occupied energy band is full. Well, that is also true because remember in insulators the highest occupied energy band is the valence band because there's no electrons in the conduction band. So the highest occupied band is full because the valence band is completely full and the conduction band is completely empty. And lastly, the gap between the valence band and the conduction band is smaller in semiconductors than in insulators. Well, that is also true because remember in the semiconductors, the band gap between the valence band and the conduction band is small, allowing electrons to jump up from the valence band to the conduction band to move about and conduct. Whereas in insulators, the band gap is so high that the electrons cannot jump from the valence band to the conduction band and conduct. So that means all 3 statements are correct, which gives us the answer E. Lastly, question 20 is a skills question, and it says the upward lift force L on the wings of an aircraft is calculated using the relationship L equals a half rho v squared times ACL, where rho is the density of air, v is the speed of the wings through the air, A is the area of the wings, and CL is the coefficient of lift. The weight of a model aircraft is 80.0 newtons. The area of the wings on the model aircraft is 3.0 meters squared. The coefficient of lift for these wings is 1.6, and the density of air is 1.29 kilograms per meter cubed. And then says the speed required for the model aircraft to maintain a level flight is. Well, remember the strategy for these kind of questions is simply just to use the equation we're given and plug in all the values that you're given. So we're trying to find the speed v, which is given in terms of v squared. So let's plug in all the other values that we know from the question and then rearrange for v squared, and then we'll have to take a square root in order to find what v is. So firstly, notice that we're given the weight of the model aircraft is 80.0 newtons, but we don't have weight in our expression here. We actually have a lift L. And we need to firstly realise that to maintain a level flight, the upward lift force must balance the weight downwards, so they must be balanced forces. So that means using this equation, L equals a half rho v squared ACL, we can say the upward lift force L is equal to the weight. So that is the 80.0 newtons, which equals a half times the density 1.29 times v squared times 3.0 for the area times 1.6. So simplifying both sides and rearranging for v squared, we get v squared equals 25.8, and then taking the square root of both sides gives us the answer 5.08 meters per second, which we can simply round up to about 5.1 meters per second, and you'll see that gives us the answer C here. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.